Hey everyone, Mr. Hauk here. In today's video, we're going to be going over the solutions to the Unit 6 practice test. Let's go ahead and get started. So for this practice test, for this video really, I've already worked through all the solutions, so I'm not going to work through them from scratch. Instead, I have all the solutions here, and I'm just going to explain the process for each problem so that this video doesn't get too lengthy. Let's go ahead and start here with number 1. And notice that my problems are probably out of order from your problems. That's because the practice test, the questions and answers were shuffled. Okay, so here's number 1. We want to check the work to solve cosine of negative 19 pi over 12. And we just want to see if there are any mistakes, which you can see there weren't any. But let's talk about why there weren't any mistakes. So we're starting with cosine of negative 19 pi over 12. And a lot of students want to say that line 1 is incorrect because how on earth do you go from negative 19 pi over 12 to 5 pi over 12? It just seems like a really odd jump, right? Well, it actually has everything to do with coterminal angles, which we talked about first semester pre-calculus. Coterminal angles are where you take an angle and you either add or subtract 360 degrees or 2 pi radians to kind of reposition yourself in the exact same spot. So negative 19 pi over 12, if we add 24 pi over 12, which by the way is 2 pi radians. I just rewrote it to be over 12 so they share a common denominator. You get 5 pi over 12. So negative 19 pi over 12 and 5 pi over 12 are coterminal angles, meaning they're in the same position on the unit circle. Okay, so this is actually a perfectly fine step. They're in the same position. They can be interchangeable basically. So what we're really trying to do now is find the cosine of 5 pi over 12. And if we look at the two angles that 5 pi over 12 gets broken into, this student chose pi over 6 plus pi over 4, which works perfectly fine because pi over 6 is 2 pi over 12, pi over 4 is 3 pi over 12. They add together for 5 pi over 12, so that step is fine. And then the student goes ahead and uses the addition formula for cosine. We can see that for cosine, if we're adding two angles alpha and beta, then the formula says cosine alpha times cosine beta minus sine alpha times sine beta. And this student does that perfectly. We can see that alpha is pi over 6, beta is pi over 4. We have cosine pi over 6 times cosine pi over 4 minus sine pi over 6 times sine pi over 4. Set up perfectly. And now we go into the actual calculating. So we want to look at the unit circle. Notice that cosine of pi over 6 is square root of 3 over 2. Cosine of pi over 4 is square root of 2 over 2. Keep the minus sign, very important. Sine of pi over 6 is 1/2, and sine of pi over 4 is square root of 2 over 2. So everything is done well. Now we check the actual multiplying. Is the square root of 3 over 2 times the square root of 2 over 2 square root of 6 over 4? Well, yes it is, because we're multiplying the square roots. There's square root of 6. Then we multiply denominators. There's the 4. Same deal over here. 1 times root 2 is root 2. 2 times 2, 4. And then finally, notice that we have common denominators of 4, so we can combine the top, square root of 6 minus square root of 2, all over the common denominator of 4. Everything checks out. No mistakes were made. All right? Now let's try the same thing with a different problem. We want to check to see if the work was done correctly to solve 39 pi over 36. Well, line 0 is fine, and really all line 0 represents is did the student copy the problem down correctly? So yeah, student copied it correctly. Everything's good to go there. Line 1 is where everything kind of gets messed up. Notice that this student is saying that 39 pi over 36 is 5 pi over 6 plus pi over 3. But if we actually break it down, 5 pi over 6 plus pi over 3, getting a common denominator of 36, well, the 5 pi over 6 turns into 30 pi over 36. That's multiplying top and bottom by 6. And the pi over 3 is 12 pi over 36. That's multiplying top and bottom by 12. But 30 pi over 36 plus 12 pi over 36 is 42 pi over 36, not 39 pi over 36. So this let me get back. This breakdown into 5 pi over 6 and pi over 3 was incorrect. It does not equal 39 pi over 36. So line 1 is where our mistake is. And also notice that we don't need to check the other lines. The instructions for the problem says to find the first mistake if there is one, so we don't need to waste time checking the other steps. We already have our answer. In problem number 3, we want to simplify tangent squared divided by secant squared plus cosecant squared. And looking at the problem initially, I don't see any identities that we can really take advantage of. So the first step, when you can't really use any identities, is usually to decompose into sines and cosines. So that's what we did here. Tangent squared of x is sine squared of x divided by cosine squared of x. Secant squared of x is 1 over cosine squared of x. And cosecant squared of x is 1 over sine squared of x. Now notice in this denominator, we want to add these two fractions, but they don't have common denominators. So we need to get a common denominator of sine squared of x times cosine squared of x. So we multiply this by sine squared of x over sine squared of x, and we multiply this by cosine squared of x over cosine squared of x. What this will do for us is we'll get sine squared of x plus cosine squared of x over the now common denominator, sine squared of x times cosine squared of x. And then we also know from our Pythagorean identities that sine squared of x plus cosine squared of x is equal to 1. So we go ahead and make that replacement. Now we're in a position to go ahead and do keep, change, flip. So we keep our numerator, sine squared of x over cosine squared of x. Change this to multiplication, and then we flip our denominator to be sine squared of x times cosine squared of x over 1. Notice now, cosine squared of x cancels with cosine squared of x in the bottom. Sine squared times sine squared gives us sine to the 4th of x. And that's going to be our most simplified. Remember that when simplifying trig expressions, the goal, if possible, is to get it to simplify down to either one trig function or a constant. Okay, and we did that. We have one trig function, sine to the 4th. All right. In problem number 4, we want to simplify secant squared of x times 1 minus cosecant squared of x. And one thing that I noticed pretty quickly is 1 minus cosecant squared, even though it's not one of these three right here, we can still rearrange to make this an identity. You know, one of those three identities was 1 equals cosecant squared of x minus cotangent squared. And notice if I take this cosecant squared and just subtract it to the left side, I get 1 minus cosecant squared of x equals negative cotangent squared. So I'm going to replace this 1 minus cosecant squared with negative cotangent squared. And that's how I continue the problem here. At this point, I've used my Pythagorean identity. I'm going to go and decompose into sines and cosines now. So secant squared is 1 over cosine squared times negative cotangent squared is going to be negative cosine squared over sine squared. Because we're multiplying, notice that the cosine squareds cancel, and all we have left is the negative sign, 1 over sine squared. And we know that 1 over sine squared is cosecant squared, and we carry the negative down with us. And again, this is going to be our most simplified version of the answer. All right, number 5. Now we start to get into some problems, very similar to some of the stuff we saw in the beginning of the unit and leading up to the quiz. So we want to find tangent of 2 theta, given that the sine of theta is 4/9 and that theta is between pi over 2 and pi. Now, first thing to take note of, if theta is in between pi over 2 and pi, that means we're in quadrant number 2. So we want to set up a triangle in the second quadrant, and we want to use the fact that sine of theta equals 4/9 to help us draw this triangle. So here's our quadrant 2 triangle. Notice the y-axis is positive. The x-axis is negative, very important. Sine is opposite over hypotenuse, so I know opposite of angle theta will be 4. Hypotenuse will be 9. We're going to use Pythagorean's theorem to find this missing leg, which, if you follow the work right here, turns out to be square root of 65. Notice, however, I make the square root of 65 negative, again, because we're on the negative side of the x-axis. So we are trying to calculate the tangent of 2 theta. And because the tangent of 2 theta requires us to know tangent of theta, let's go ahead and calculate that real quick. Well, we know tangent is opposite over adjacent. So opposite of angle theta is 4. Adjacent to angle theta is negative square root of 65. So we have 4 over negative square root of 65. We don't normally or really ever like square roots and denominators. So let's rationalize it by multiplying by root 65 over root 65. So this gives us the tangent of theta, negative 4 root 65 over 65. And And that's what I'm going to plug in to each of these tangent thetas. So we have 2 times negative 4 root 65 over 65 over 1 minus negative 4 root 65 over 65 squared. Don't forget that squared. Going through and simplifying, treat this 2 as a 2 over 1. So 2 times negative 4 root 65, that's negative 8 root 65. Denominator is still just going to be 65. And then this little piece, which looks a little intimidating, really isn't all that bad. We're taking this negative 4 root 65 over 65, and we're multiplying it times itself. Let me do this in red. Okay, we're multiplying this thing by itself. And if we think about that here, negative 4 times negative 4, that's 16. Root 65 times root 65, well, it's the same thing under the square root, multiplied to itself. That's just going to be 65. The square root falls off. And then in the denominator, 65 times 65. Well, if I write it like this, notice that 65's cancel. All we'll have left is 16 over 65, which is what I've carried down to right there. Okay, so let's get rid of that. It looks a little messy. All right, so this is what our problem is simplified down to. And we want to go ahead and get common denominators in this denominator of the fraction. So I'm going to multiply this 1 times 65 over 65. Doing that, we have 65 minus 16. That's going to give us a 49. Common denominator of 65 right there. And we already had a denominator of 65 right here. So notice that, fraction over a fraction, denominators are the same. They're going to cancel each other out when you do keep, change, flip. So let's go ahead and cancel them out now. And this will give us negative 8 root 65 over 49, which is our final answer. All right, problem number 6. We want to find the sine of 2 theta, given that the tangent of theta is negative 3/5 and that theta is between 3 pi over 2 and 2 pi, which, by the way, means that theta is in the 4th quadrant. So setting up our 4th quadrant triangle right here, notice the x-axis is positive, the y-axis is negative, very important. We know that tangent is negative 3/5. That's opposite over adjacent. So opposite leg, the negative 3. Adjacent leg is going to be positive 5. If we follow through with the Pythagorean theorem to find the missing side, which is the hypotenuse, we get that the missing side is square root of 34. Then we're just going to follow the formula for the sine of 2 theta. Sine of 2 theta is 2 sine of theta times cosine of theta. Well, sine of theta, remember sine is opposite over hypotenuse, that's negative 3 over square root of 34, right there. And cosine of theta is adjacent over hypotenuse. That's going to be 5 over square root of 34, right there, okay? Now, I know that we say a lot, you don't want square roots in denominators, but if you look at this problem, if you kind of look ahead a step, you can tell that when we multiply these denominators, square root of 34 times square root of 34, they're going to turn into 34 here. Okay, so that's kind of why I left the square root in the denominator. I could see that they were going to get rid of the square roots themselves. All right, but multiplying the numerators up top, 2 times negative 3 times 5, that's negative 30. Square root of 34 times square root of 34, that's 34. And negative 30 over 34 will reduce to negative 15 over 17. And that's our answer. All right. Next, find the cosine of 2 theta, given that the cosine of theta is 3/7 and that theta is between 0 and pi over 2, meaning that theta is in quadrant 1. So here's our quadrant 1 triangle right over here. We know in quadrant 1 the x's and the y's are both positive, so that's nice. Makes our job a little easier. And let's go ahead and use the fact that cosine adjacent over hypotenuse, there's the 3, the adjacent, hypotenuse, there's 7. If we follow through Pythagorean's theorem, we get that this is going to be 2 square root of 10, okay? So now we're going to go through and calculate cosine of 2 theta, which we have some options, right? Cosine of 2 theta actually has 3 different formulas that we can use. I just picked the first one. It doesn't really matter. You can use whichever one that you want. You'll get the same answer. I just did cosine squared minus sine squared. So cosine of theta, adjacent over hypotenuse, that's going to be 3/7. Make sure you square it. Sine of theta, opposite over hypotenuse, 2 root 10 over 7. Again, make sure you square it. 3/7 squared, remember that when you're squaring a fraction, you square the numerator and the denominator. So that's going to be 9/49. Same deal here. 2 root 10 over 7, square both numerator and denominator. 2 root 10 times itself, 2 root 10, would give you 4 times 10, which is 40. So we have 40/49. And then we see that we have common denominators, so we can subtract the numerators. 9 minus 40 gives us negative 31/49, which is our answer. All right, problem number 8. This is going to be a double triangle problem. We can tell because we have 2 domain restrictions right here. Domain restriction for triangle A, domain restriction for triangle B. So let's go ahead and look at these 2 triangles. We know that the sine of A is 7/25, and that A is between pi/2 and pi. This is telling us that A is in quadrant number 2. So let's look at this triangle here in quadrant 2. Now, because the sine is 7/25, we know sine is opposite over hypotenuse. If we do Pythagorean Theorem, we get that the missing leg is 24. Notice that I'm making sure to make it a negative 24 because we're on the negative side of the x-axis in quadrant 2. For the other triangle, we were told that the tangent of B is 4. Now, if the tangent of B is 4, and we know tangent is opposite over adjacent, then the sides of the triangle, opposite has to be negative 4, adjacent has to be negative 1. They both have to be negative because they're in quadrant 3. Those are negative x values and negative y values. And it just makes sense because, again, tangent is 4. Negative divided by negative is going to give you the positive 4 there. Following through Pythagorean Theorem, we're going to get our hypotenuse to square root of 17. Now we're going to use these triangles to make the calculation of cosine of A minus B. So following the formula, cosine of A minus B is cosine A times cosine B plus sine A times sine B. Cosine of A, so if we look at triangle A here, I'm calling it triangle A, by the way. It's the angle A, but I'm going to call it triangle A. But looking at this triangle, cosine of A, adjacent over hypotenuse, that's negative 24/25. Cosine of B, adjacent over hypotenuse, negative 1 over square root of 17. Over here, sine of A, opposite over hypotenuse, 7/25. Sine of B, opposite over hypotenuse, negative 4 over square root of 17. And there's a little typo. Let's fix this real quick. It should be square root of 17 right there. Okay. Now let's multiply and simplify. Negative 24/25 times negative 1 over root 17. That's, double negative. We're going to get a positive. 24 over 25 root 17. Over here, 7 times negative 24. There's our negative 28 over 25 times square root of 17. Common denominators, which are nice. So we can really go ahead and add the numerators. 24 plus negative 28. That's going to be negative 4. Denominator stays the same. 25 root 17. However, we don't like this as an answer. We have a square root in the denominator, so let's rationalize it by multiplying by root 17 over root 17, which is going to give us negative 4 root 17 on top, and then 425 on the bottom because root 17 times root 17 is 17, and 17 times 25 is 425. Really good problem. Make sure you know how to do this. All right, and then numbers 9 and 10, these are the last 2 problems. These are going to be, check the work kind of problems. And for this one, we want to verify, or we want to check the work that the student did to verify that cosine squared of x times 1 plus cotangent squared of x is equal to cotangent of x divided by tangent of x. So let's see if they did the steps correctly. First, line 0. Line 0 is just did they copy it down correctly, which they did. Line 1. This student is saying that 1 plus cotangent squared is equal to cosecant squared. That's correct. That's one of our Pythagorean identities. In line 2, the student is saying that cosecant squared is 1 over sine squared. That is also correct. In line 3, they went ahead and multiplied cosine squared times 1 over sine squared to get cosine squared over sine squared. This is good. Remember, if you need to, imagine that cosine squared over 1. It'll help with the multiplying. Okay, after that, the student is saying that cosine squared over sine squared is cotangent squared. That's good. Then the student is breaking the cotangent squared into cotangent x times cotangent x. That's perfectly fine. That's what cotangent squared means. And then the student is saying, okay, well, let's take one of these cotangents and let's rewrite it as 1 over tangent. We know that to be true. We know cotangent is 1 over tangent, as well as cosine over sine. But the 1 over tangent is useful for us because then we can multiply cotangent x times 1 over tangent x to get cotangent over tangent, which finishes the proof. So there were no mistakes made in this verification. And also, by the way, one thing to keep in mind, I've had to tell many students this, when you're checking over, when you're doing these check over the work to verify problems, you shouldn't be asking yourself, is this what I would do? You should be asking yourself, are the steps that were taken correct? Okay? And even though this might not be what every student would do solving a problem like this, the steps were done correctly. Here's our last problem for this practice test. We want to check to verify that tangent of theta plus cotangent of theta equals secant theta times cosecant theta. We want to check to see if this student did the right work. Okay, so step 0, or line 0 rather. Did they copy the problem correctly? Yes, they did. Line 1, they are decomposing tangent into sine over cosine, which is fine. Cotangent into cosine over sine, also good. So that step is fine. Step 2 is where they lose it though. Notice that in step 2, they combined these fractions, they added them. But you can't do that because these fractions don't have common denominators. One is a cosine, one's a sine. So if you were going to add these together, then what you had to do was you would have had to multiply this by sine theta over sine theta, and this by cosine theta over cosine theta. But the student didn't do that because you can see the top is still just sine theta plus cosine theta. So you can see that these didn't get multiplied by anything. So this is where the mistake is. Okay, and again, we don't need to continue any further. We found the first mistake. Don't waste time. Move on to the next problem. Okay, so those are the 10 problems from the practice test. Hopefully it didn't seem too bad. I know some of the calculations were a little challenging, especially in these kind of double angle problems or these sum and difference problems, but that's just the nature of this unit. Okay.